Hi guys, welcome to Origit's computer classes once again. So till now we have discussed two sorting techniques, that is bubble sort and insertion sort, right? So today we will be discussing another sorting technique, that is selection sort. Okay, so like the previous two sorting techniques, this will also follow the O of n square time complexity, but the process is somewhat like bubble sort. But the thing is that in bubble sort, the largest element used to reach the end of array first. Here the smallest element, the lightest element, will reach the first index of the array first. Okay, I mean the lightest element will come to the first position first. Okay, so this is the technique of selection sort. Now, why selection sort? The name, see what it does, it actually selects elements one by one. Say suppose it selects the first element. Okay, now it is obvious that the first element is not at its correct position. So what will another pointer do? We will use another pointer. Okay, this is a j. This element, the first element where I is pointing, will be compared with each of the element in the array. Okay, then it will find out what should come, what fits best for this index. That means actually what is this I doing? This I pointer selects indexes. Okay, that is why it is termed as selection sort. Selects the indexes and finds out its best element. Okay, fine. Okay, so I pointer is for comparison. It will not for comparison, it's for selection. It selects each indexes one by one, and this j will compare each of the element, and this j will find out the best element and place it in that index. So let us see how it works. So first I is pointing at 0. So at index you have 72. Now j starts comparison. So what will j do? Is this element where j is pointing, is it greater than 72? No. So that means ARR of I, that means this element and this element, if you compare, so 72 is greater than 35, right? That means 35 should take its place. Thus we swap them. So 35 comes here and 72 moves here and j moves one index next. Okay, done. Again, so 35 is now present here. Now 35 will be compared with the other elements. So is 46 greater than 35? Yes, that is true. That means 35 and 46, I mean 46 should come after 35, and so therefore that is okay. J moves to the next index. Is 88 greater than 35? Or I mean is 35 greater than 88? No. So 35 is less than 88 and it is coming before 88, so it is okay. Fine. Now 20. Is 35 greater than 20? Yes. And now is 35 coming after 20 in the array? No. Therefore we swap them. Swap these two. 20 comes here, 35 moves here, and j proceeds to the next. Okay, done. So now J again. 31. Is 31 greater than 20, or I mean is 20 greater than 31? No. So 20 is less than 31. It is coming before 31. So it is absolutely fine. Now here this is the end of our first pass. At end of first pass, this is our array. A is equal to, we can say it is 20, 72, 46, 88, 35, 31. And now what we can say is this 20 is currently at its correct position, right? Because I was pointing at that element, and J has compared it with each of the elements. See, 20 is the smallest element, and smallest element has come to the front end of the array, right? So this is, I am marking it as black, and now I points to 1. Okay, and J starts from I plus 1. Now, so this element 20 is now out of comparison. This 20 won't be compared with anyone. So as it is now in its perfect position. Fine. Okay. So now J again 46 is 46. I mean now I is pointing at index 1 and 72 is present at index 1. Is 72 greater than 46? Yes, and it is coming before 46. Therefore swap them. 46 comes here, 70. Okay, and J proceeds to the next element. Is 46 greater than 88? No, 46 is not greater than 88, definitely. And 46 is coming before 88. Fine. So J moves to the next. Is 46 greater than 35? Yes. So 46 should come after 38. So we swap them. Just take it. 46. And J moves to the next one. Is 35 greater than 31? Yes. So 35 should be swapped with 30. 30. Right? So this is the end of our second pass, and at the end of second pass, we are left with this. Okay. So this is our array, and we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Yeah. So here we have 20, here we have 31. Okay. Now 72, 88, 46, 35. 0, 1, 2, 3, 4, 5. And now I points here. Okay. And J starts from I plus 1, so from index 3. Fine. So at the end of second pass, the second lighter element, the second most light element comes at its correct position. So we are just selecting each indexes and bringing the correct element for that index. Fine. So as per our observation, what can we say? There are two observations. One is I is selecting an index. This is fine. This was our first observations. Second is J is starting from I plus 1. Right? These are the few observations. J is starting from I plus 1. Okay? Fine. right? Okay, so second observation is J is starting its comparison immediately after the i's index. Okay, J is I plus 1. Fine. Now, what is our third observation? We are comparing each of the element under this J. What this J is doing actually? It is comparing each element. So, with which element it is comparing? All the elements of the array. So, the ith element, right? That means whenever the element at index I is greater than the element at index J, like we did here. Okay, so J here 88 and I is 72, so nothing is being done. 46, okay, 46 is 72 greater than 46? Yes, that means we are swapping them, right? That means, see, observe carefully, whenever element at index I is greater than the element at index J, we are swapping. Okay, so swap them. That means, so what can we do? If A of I is greater than A of J, what are we going to do? Swap A of I and A of J. Yes, this is what we are going to do. Swap A of I and A of J. Fine. And just this is the process. So follow these steps again. So read these observations again and see, is it happening? So 72, now J moves to the next index, is again, so as per this condition, if A of I is greater than A of J, okay, A of I 46 and greater than A of J, the condition is true, so swap these elements. Okay, very good, 46. Fine. And also third is update J. Okay, update J. And obviously when J ends, update I. Okay, that is J plus plus and I plus plus. So this is the end of second pass, right? And at the end of this is the end of third pass, right? Third pass, because at the end of second pass we had another sum from this array. Okay, so at the end of third pass, we are left with this. Fine. So we can have 20, 31, 35, right? And we have 88, 72, 46. Fine. Okay. 0, 1, 2, 3, 4, 5. Now, again if you see, so I starts from, so these elements will be again ignored because they are already been sorted. I starts from here, J starts from here. Is 72 greater than, is 88 greater than 72? Is A of I 88 greater than A of J? Yes, so swap them. 72. Okay, and J moves to the next index. Is for 72 greater than 46? Yes, swap them. 56, 70. Okay, and thus at the end of fourth pass we are left with this array. Okay, so this is at the end of fourth pass. Fine, at the end of fourth pass. A is 20, 31, 35, 46. Okay, and just two elements are left to be sorted. Of course they will be 88, 72. Okay, and I points here, J points here, and just swap them because only two elements are left. We can see that 88 is greater than 72. Swap them, and our array is sorted. Our array becomes sorted. Okay, so thus this is what selection sort is. We are selecting each index at a time, and then we are just swapping, finding the best element for ith index wherever I is pointing. Okay, and J is doing the computations. So looking at these observations, can we write the code? Yes, we can do it. These observations are enough, right? Okay, so let me erase this. Okay, so now if you just move back a bit, the array where we ended, the I last pointed at index n minus 1, right? I mean last pointed at n minus 2, because the n was 6 there in the array. N was 6 and it was pointing at 4, and J swapped it finally, right? That means, so I better we keep it, I moves up to, we can say I nz n minus 2. Okay, and J nz n minus 1. Yes, so seeing this, looking at this observation, we can write that. So let us take a function, say void selection sort, void selection sort, and it is taking two arguments, the array. Okay, it is taking the array. Okay, just the array. Okay, and the size is taking the array and the size int n. Fine. Now, so n is the size, other is the array. Now let us look at the observations. I selects indexes, find out the base element. Now from where does I start? Definitely from index 0, because anytime either it will start from the end or it will start from the first, and we have seen in our case I started from the first index, right? So for int I is equal to 0, now I less than, I ends at n minus 2, right? So you can either write I less than equal to n minus 2 or I less than n minus 1. Fine, I less than n minus 1 and I plus plus. Fine, because I at the end updates by 1. Then again the second observation is J starts from I plus 1. Okay, that means J starts from, J is equal to I plus 1. Initially J is equal to I plus 1, and J is ending at n minus 2, right? Now sorry, J is ending at n minus 1. That means either we can write J less than equal to n minus 1, or better you write, to look good, J less than n. Fine, same thing, because less than means before n, just 1 before n up to, it can be true, and J plus plus, opening brace. What is our third observation in this case? So whenever our a of I was greater than a of j, so write it as it is. If a of I is greater than a of j, English as it is, then what are we going to do? Swap a of I comma j. Either you can write another swap function, okay, and then call that function here with swap a of I comma j. As here I am not writing, so what I am doing, I am just using swap using third variable, okay, swap them using third variable. So say I am taking a variable, say temp, int temp, okay, or you can declare this variable before, int temp here, int temp, temp is equal to a of I, a of I is equal to a of j, a of j is equal to 10, fine, right? That's all. So closing of your if, closing of your j, closing of I, closing of the function, done. You are done with this. So this is the code. You can just find out from the observation, because after this update j, j is already updating as per for loop. Then what to say, j ends, j is ending here, and then I will update finally, closing of I loop and closing of the function. Thus this is the code of selection sort, okay. You can write this code in your system and check. Also you can do a dry run of the code. Thank you. Okay, so this was your code for selection sort, okay. So I travels from 0 to n minus 1, then j I plus 1 to n. Now talking about the time complexity of this code. So at its worst case, when an array is arranged in reverse ascending order or descending order, you can say. So say this is our array arranged in reverse ascending order, say 3 elements, 3 to 4 elements I am taking, 1, 2, 3. So say 72, 66, 55, 30. Now when I is here and j is starting from here, so at worst case when reverse sorted, so each time j moves, j I will compare with each element, j will compare with the ith element, and they need to be swapped. So say 66 is swapped with 72, again j moves, 55 again swapping required, 55, 66, j moves, 32, it needs to be swapped, okay. Right, again j I starts here, j. So see, consequently for ith element, every time the elements coming after I needs to be swapped with I, right? So here I am taking 4 elements. If say n is very large, so that is a problem. But what to do? The time complexity of selection sort. That means I is traveling the whole array and j is traveling the whole array. So at worst case scenario, time complexity is big O of n square, right? Because I is traveling n times, big O of n square, I is traveling n times, and j is also traveling n times, right? Now, best case scenario, say the array is totally sorted, okay? So the array is totally sorted. So 32, 35, 88, 89, okay? So j is traveling up to n, I is starting from here, j is starting from I plus 1. So now no need of swapping, but the comparison goes on, right? J stops here. So what one thing can we do? Still till now time is required is big O of n square, because the loop will comparison will be done. J will stop again, the I will start from the next element. So why to go for so much so much time, okay, so much extra iterations? Better what we can do, we can take one variable, say swapped equal to 0, right? And here we can do swapped equal to 1, just like the bubble sort case, right? So at any moment, see, either of the thing, at any moment, if the array is not arranged properly, so swapping will be required at some point or the other. But if swapping is never required in a particular iteration of j, this swap will never turn 1, right? Then what can we write outside here? So if swapped equal to outside j, if swapped equal to 0, then we can break, right? So I loop will stop. So what maximum, at max j will run for once. If you, so at optimized best case, there are two things. Best case, in the case of best case, so if optimized, time complexity is big O of n, okay? Otherwise time complexity is big O of n square, right? At an average, okay, not exactly n square, because j is starting from I plus 1 every time, so not exactly n square, but at an average we can say it's n square, okay? And average case is definitely it's big O of n square, just the thing we did, any array at random you take, okay? So this was about the time complexity of selection sort. Thank you.